160 meter was the lowest radio frequency band allocated to radio amateurs before the adoption of 630 meter and 2200 meter bands by many countries in the beginning of 21st century. It has been popularly called as the top band, maybe because it is on top of the medium wave broadcast frequencies. 160 meter has also been nicknamed the gentleman's band. It is actually a medium frequency band if you go by the definition of 300 kHz to 3 MHz for medium frequency. Allocation in the 160 meter band for radio amateurs in India, according to the National Frequency Allocation Plan 2022, is 1800 to 1825 kHz. In some other regions, allocation is given up to 2000 kHz. I have absolutely no space for a half-wave dipole antenna for 160 meter. Hence, I thought of a loaded coil dipole with 121 microhenries on each side. I used the online calculator to find dimensions. Antenna length before the coil was calculated as 12.5 meter and that after the coil as 7.5 meter on each side. Soldered the joints to coils one by one. There were 2 joints to be soldered on either side of the coil. I did not solder the feed point as I am planning to homebrew and attach a voltage balun later. After a lot of effort, the coils and antenna elements are ready. I am using 15 meter of RG213 cable as feed line. The feed point region was then mounted at 5.5 meter from ground on a galvanized iron pipe using nylon rope. After mounting, the rather heavy loading coils were supported using additional nylon wires to prevent the antenna from sagging too much. One end of the antenna was at 3 meter and the other end at 2 meter from ground due to mounting constraints at home. Earlier, I used to test the SWR on various bands using my radio and or SWR meter. Now that I have a nano VNA, I prefer to use it first. Moreover, it gives more information than just the SWR. Currently, I use the Smith chart in nano VNA to decide whether my antenna elements have to be shortened or lengthened. I am calibrating my nano VNA for testing the new 160 meter loaded coil dipole antenna. This is the jumper cable with male SMA connectors at both ends and a female to female SMA connector attached in addition. I am going to set the frequency range . That is stimulus. Stimulus we have to set the start. I am putting it as 1 megahertz. It has come as 1 megahertz here. And stop, I am putting it as 11 megahertz because I want to check the harmonics also. It has come here, 11 megahertz has come here. Now I have to calibrate. For that I will be connecting the open load first. I have not connected. This is the open, SMA open connector. Open has been connected. I have calibrated for SMA open. This is the SMA short connector. So SMA short has been connected, I have to calibrate. It has been calibrated and the highlighting has shifted to load. This is the SMA 50 ohms load and I am going to connect. SMA 50 ohms load has been connected, and you can see that the SWR is shown as 1:1.02 because that's a dummy load. Now to calibrate for the load. Calibration for the load is done. Now I'll skip through the other things. So it's over. Now I will save to SD card. I will save it in memory 6. So it has been saved to memory 6. Now using an adapter that is SMA male to SO239 adapter, I have connected the PL259 here. That is, this is coming from my 160 meter loaded coil antenna, and you can see that there are several dips. One is here. This is one dip in SWR. It's a very high SWR here. Another high SWR, another dip, another dip, another dip, and another very high here. So we will see which are these dips in SWR. They are the resonant points. I have used the top button. There is a button here which can be used to change the marker. With this marker here now, I can see that 1:2.1 SWR is there at 10.8 megahertz. That is nearly the 30 meter amateur radio band. But above that, band is not as high as 10.8. Now I am bringing the cursor. The highest SWR here is 5 or 6. I don't want to know about it. This seems to be the next lowest SWR at 7.8 megahertz. Again, above the amateur radio band. It's above the 40 meter amateur radio band. There is another dip here at 7 megahertz with SWR 1.285. If I am lucky, I will be able to tune this for the 40 meter amateur radio band with my automatic antenna tuner, because up to 3 SWR the antenna tuner, automatic antenna tuner in FT710 can take care of. So I may be able to operate with this antenna in the CW segment of 40 meter band, but still the SWR is not that good. This is another dip in the SWR, about SWR of 1.135. That's the least in this situation, as it is occurring at 4.9 megahertz. That is near the 5 megahertz or 60 meter amateur radio band. The next dip is with 1.39 or 1.4 SWR at 3.3 megahertz. Unfortunately, that is about 200 kilohertz below our amateur radio band of 80 meter. If it was a little more higher, then I would have been lucky to operate on 80 meter. Let me see what happens on the 80 meter band. 3.5 megahertz. There is SWR above 4. So if I want to operate, the internal antenna tuner may not be sufficient. I'll need an external antenna tuner for that. Now, what is happening at the so-called 160 meter band for which I made this antenna? See, the SWR is 6.4 for 1.8 megahertz. So as of now, I won't be able to operate on 160 meter with this antenna. I'll have to change the dimensions or some other modifications I'll have to do. Then only I'll be able to operate. The SWR is quite high, beyond the tunable range. I have changed the frequency range from 1.5 to 2. That is so that it will include the amateur radio 160 meter band in the center, and I am seeing that the SWR is high there. Now I'll see what I can do with the Smith chart. This is the Smith chart. You can see that the tracing here is lower down. This is the center line, and this is the point which represents 50 ohms impedance. And you can see that the impedance resistive value is 13.41 here, and the capacity value is 41.72. That means anything below the baseline, the antenna is capacitive, and anything above the, that is this graph, green graph, Smith chart graph, if it is below the baseline, that means antenna is capacitive, meaning that it is shorter than what is needed. And if it's above, you can see that it will be inductive, the antenna length is more. So from the Smith chart, I have found that the antenna impedance is very low, resistive component is low at 1.78 megahertz. I'll change to 1.810. That is the middle of the 1.8 megahertz amateur radio band. I have increased the length of the antenna by 50 centimeter on either side, which is the maximum I can, because the length was folded back only 50 centimeter, and the upper resonant point is at 10 megahertz itself with an SWR of 1.885. Next resonant point is at 7.8 with SWR of 1.215. There is a minor resonance at 7 megahertz with SWR 2.95, which I may be able to use with antenna tuner, built-in antenna tuner. The next is 4.9 megahertz with a fairly good SWR 1.3. The best SWR is again at 3.2 megahertz, which is below the 80 meter amateur radio band with SWR 1.35. If I go to the 80 meter band, the SWR is 5.3, for which I'll need tuner, external antenna tuner to work. Coming to 1.8 megahertz, which is my region of interest for 160 band, 160 meter band, SWR is still 6.4. I won't be able to work without an external antenna tuner. There is another dip here that is at 1.1 megahertz, again not useful for me. This is the Smith chart. I have brought it to the middle of the 160 meter band. Again, I can see that the resistance is 12.84 and the capacity value is 40.16 ohms, or capacitive reactance, because anything below this horizontal line will be taken as capacitive reactance, meaning that the antenna is shorter than what it should be, and if it is above, it is inductive reactance, meaning that the antenna is longer. So lengthening my antenna by 50 centimeter has not done much, because this is an antenna meant for 160 meter band. So 50 centimeter is nothing for that band. That is probably why there is not much of a difference in the Smith chart. It is way below the horizontal line. So for me, it is not possible to lengthen further as my space constraints have been reached. Maybe I'll have to change the location of the coil or increase the inductance of the coil. those are the two options available for me.